now going to look at something called Newton's method, and as the name implies, it was developed by Sir Isaac Newton, and it is designed to be used to find the solutions to equations, in particular, to find the zeros of an equation of a function. The principle behind it, at least graphically speaking, looks a little bit something like this. If you had a function, f of x, it's coming up and crossing the x-axis at some point, and you're trying to find that point, you're trying to find that x value, then if, let's say for the sake of argument, that it was a difficult to solve function, something that's either difficult or perhaps even impossible to solve algebraically. The idea here is that you would make pretty much just a guess, a fairly random guess. So you're going to say, I'm going to guess that the zero, the x-intercept is at some number x sub 1. Well, you come up on the function to the corresponding point, and by corresponding point, I mean x sub 1, y sub 1, and you construct the tangent line to the curve at that point. All right, and what the assumption is, and actually typically the reality is, the intercept of the tangent line is much easier to find than the intercept that you're actually looking for. Because remember, with your tangent line, you're going to be dealing with a linear equation. There's not a lot out there that's easier to solve than a linear. So you will find that point of intersection. We'll call it x sub 2. And as you see, there's going to be a progression here. You're going to make a guess and use a tangent line to make a second guess. With that second guess, you would construct another tangent line. And that tangent line would be your third guess. And the plan is, the hope is, that the intercepts for the tangent lines are going to get closer and closer and closer to the point in question, the point that you want. After just 3 here, I've gotten so close to that point that it's practically impossible to distinguish the two. Now, this procedure, though, be aware, just right up front, be aware that this procedure isn't perfect. It doesn't work every single solitary time. Okay, there are instances where, and it's a little bit hard to draw, but I'll make an attempt. But there are instances where, if you're looking, say, for this point right here, all right, that particular intersection, that one tangent line, you make your guess, and let's say your guess isn't perfect. Let's say we make a guess right here. This is our x sub 1, and the tangent line that goes with that bumps us up here. And there's your second guess, and the second guess bumps us right back, and I'm going to have to fudge it a little bit because, again, I'm not the best artist. But if the second guess bumps you back to the first guess, then what you've done is you put yourself into a loop. All right, so it is possible just basically to be bouncing back and forth between guesses and not really getting any closer. And the best thing to do in a situation like that is just scrap it and start with a brand new first guess. All right, there's really no way to recover from that than just forgetting about the first guess and trying it all over again. All right, so what does the algorithm look like? Well, again, you could just look in your book and memorize it, or we can develop it from scratch. All right, we start with something that should be familiar to you from your Algebra 1, Algebra 2 days, and that is the point slope version of the point slope equation of the line. All right, so what we're going to do is, first of all, walk through the steps of coming up with a tangent line. And that's actually pretty simple. all you're going to do there is, instead of calling it m, we're going to call it f prime of x1. And so that, because that's how you find the slope of the tangent line, is to take the derivative of the function at that x value, right? So this would be the equation of the tangent line to a function at a point, all right? The next thing we're going to do is we're going to assume that we're looking for an x-intercept. Well, when you find an x-intercept, you plug in a 0 for y. So we'll do that. All right. And then the next thing is your y value is going to be determined by the function. So this becomes all right. And the next x we're looking for is going to be the x value that corresponds to this y-intercept. So this x actually becomes x sub 2. Because again, it's the next x, not just any x, because when it was written, it's just an arbitrary x. It's any x on the line. We are in particular looking for the next x, which is the one that corresponds to the y-intercept. I will then divide off prime of x, like so. Then I'll move the x sub 1 to the other side. And there you go. All right. So that is Newton's method when you're stepping from your first guess to your second. If you want to expand this to general terms, the next guess is always going to be equal to previous guess minus the function value at the previous guess divided by the derivative at the previous guess. So this is basically the algorithm that is used with Newton's method. All right, so let's put it to use. All right, let's put it to use and actually work a problem here. All right, let's say that the equation I'm trying to solve is f of x equaling x cubed minus 2x minus 5, and I want to set f of x equal to 0. So basically, therefore, the equation itself is x cubed minus 2x minus 5 equals 0. This is what I'm trying to solve, and this is the function that I will use to solve it. And let's just go with a first guess of 2. All right. All right. Therefore, as I've already stated, the f of x is the x cubed minus the 2x minus the 5. The f prime of x would be a 3x squared minus 2. All right. So the algorithm, therefore, will say your next guess is equal to your last guess, all right, minus f of x sub n will be x sub n cubed minus 2 times x sub n minus 5 over f prime of x sub n, which is 3 times x sub n squared minus 2. All right. Now you could do this by hand, okay, but I am definitely not in favor of making things harder than necessary. So I would always believe in putting these things into the calculator. We're not living in Newton's days where we have to use a quill for everything. So on the calculator, you're going to put in, for the algorithm part, x minus, and then in parentheses, x cube minus 2x minus 5, close parentheses, because that's the top of the fraction, divided by, open parentheses for the bottom of the fraction, 3x squared minus 2, and don't forget to close the parentheses. All right. So I will go to my table setup, and set it to the ask option and then to the table. It requested that we make our first guess a 2. So I'll put in a 2 and then get out 2.1. All right. So my first x value is 2. That's my x sub 1. My x sub 2 is 2.1. To get the next guess, I put in the last guess. To get the next guess, I put in the last guess. And as you can see here, they've already started to match each other. All right. As soon as these numbers match each other, then it would be redundant to go any further. All right. So the last output is a 2.094551, etc. All right. And so that is the best guess, the best approximation according to Newton's method for the solution to that equation, for the zero of that function. All right. There are other problems that can be solved with this that aren't exactly equation solving problems. For example, if it asked you, what's the 6th root of 2? Now, I know you can put this into a calculator. I get that. But this can be done with Newton's method. All right. Now, I'm going to do it. I say you can just plug 6 root 2 in the calculator. We all know that. You can just ask the calculator to take that root. But this can be turned into something that, even though you put it into your calculator, could have been done by hand. All right. So the 6th root of 2, the equation that goes with that is x to the 6 minus 2. Oops, didn't write it. The equation that accompanies that, if we say 6th root of 2 is equal to x, then you raise both sides to the 6th power and you get x to the 6 equals 2. Therefore, x to the 6 minus 2 equals 0 is the corresponding equation. If you can solve this equation, you know that number. So why is it preferable to solve this equation? Because this equation has a polynomial in it. It's taking the roots completely out of the picture. Polynomials are by far easier to work with. All right, so for this one, my f of x is going to be x to the 6 minus 2. My f prime of x is going to be 6x to the 5th. Therefore, my algorithm says that the next guess is equal to the first guess minus f of x sub n would be x sub n to the 6 minus 2 over f prime of x sub n would be a 6x to x sub n to the 5th. So back to the calculator for that one. Clear out the old and put in x minus, and in parentheses, x to the power 6 minus 2 over 6x to the power 5, and close the parentheses, and wonder what the guess would be. Well, for your first guess, if you think about it, x to the 6th is going to be a large power, large number. So the 6th root is going to be a pretty small number. All right. So my first guess would probably be something like 1. So I put in a 1 right there. I go to my table and put in a 1. And actually, let me just delete out these old ones. And I get a 1.1667. And if you want more accuracy than that, just highlight it. And you see it's actually a repeating 6. Okay, so I jump down, 1.1667, put it in again. And for my next guess, I get 1.1264. And for the next guess, 1.1225. And as soon as it starts to repeat, you're basically done. All right. And you can go over here again and highlight it and see a lot more decimal places. See as many decimal places as you want. All right. So the first one was an example of solving an equation that would be difficult to solve. Second one was a root that would be difficult to evaluate without calculator help. And again, I know you're going to say, well, you used a calculator right here. Well, with this algorithm, I could have done it without a calculator. It wouldn't have been fun, but this is definitely doable without a calculator. These powers and division and so on and so forth, you could do that without a advanced calculator. All right. There are equations that are also practically impossible, dang near impossible to solve without a calculator. And without the calculator, it's impossible to solve them without Newton's method. So if I had cosine of x equal to x, if I want to know when does the cosine of a value equal to that value, I would write that as cosine of x minus x equals 0. That makes my function cosine of x minus x, and my derivative negative sine of x minus 1. Right? So algorithm says x of n is going to be equal to x of n plus 1. The next one is equal to previous minus f of is cosine of x of n minus x of n over negative sine of x of n minus 1. Okay, that's again what the algorithm is going to look like. And so, onto the calculator, clearing out everything that was there. I'm going to put in an x minus, and then in parentheses, cosine of x minus an x, close parentheses, divided by the denominator is a negative sine of x minus a 1. Close those parentheses, go to the table, and let's just start making some guesses. Now, there may be numbers you can't put in. If you were to put something in right here that would create division by 0, your algorithm would crash. All right, so be careful of that. Do not put anything in right here that would cause division by 0. All right, so anyway, I put in a 0, got out a 1. Put in a 1, get out a 0.99985. Put in 0.99985, and it's already started to repeat itself. Okay, so with this one, what you're going to find with a lot of these is more than one answer. Okay, there's more than one answer for a lot. And with this one, if you wanted to check that answer, oh, let me check one thing. Almost. Look at what I did. That was dumb. I was in degree mode because of my other class. I was looking at that answer thinking that was a little bit weird. All right, let's go back. Word to the wise. Always make sure you're in radian mode. Okay, let's try that again. Put in the 0, get out a 1. Put in the 1, get in. That looks better. 0.75036 and 0.73991 and 0.73909. And there it started to repeat itself. Finally, x equals 0.73909. Again, word to the wise, always make sure you are in radian mode. If you're doing other things that require degrees, like I was a little while ago, make sure you switch back. Make sure you switch back to radians before you do any calculus. Even if you're teaching a pre-calc class, make sure you switch back to radians before you do calculus. All right, so there's the ins and the outs of Newton's method. Pretty easy method to use, especially with calculator help.